Have you ever wondered if, during a long drive, your speed at some exact moment matched your average speed over the whole trip? Well, in mathematics, there's a powerful theorem that guarantees just that, not for cars, but for functions. It's called the mean value theorem. The mean value theorem is one of those elegant results in calculus that connects the average behavior of a function with its behavior at a single, specific point. It tells us that no matter how a curve twists or turns, as long as it's continuous and smooth, there is always at least one point where the slope of the tangent line matches the slope of the overall secant line, in other words, where the instantaneous rate of change equals the average rate of change. This theorem is not just a theoretical curiosity. It's a cornerstone of calculus, with deep implications in physics, engineering, economics, and more. In this video, we're going to explore what the mean value theorem really says, understand its geometric meaning, see how it connects to Rolle's theorem, and walk through a full proof with clear, simple steps. So whether you're a math student, a curious learner, or someone who just loves the beauty of mathematics, stay with me, because what you're about to see is one of the most insightful and useful theorems in differential calculus. So how we can prove that? Let's consider a function, f, which is continuous on the interval from a to b, and differentiable inside that interval, meaning between a and b, but not necessarily at the endpoints. Our goal is to prove that at some point c between a and b, the derivative of f at c, that's f prime of c, is exactly equal to the average rate of change of f between a and b. That is, f prime of c equals f of b minus f of a, divided by b minus a. To do this, we'll build a helper function. Let's define a new function called u of x. We set u of x equals f of a, plus the average rate of change, that is, f of b minus f of a over b minus a, times x minus a. This function u is just the equation of the straight line passing through the points a, f, a, and b, f, b. In other words, it's the secant line. Now, let's define a new function g of x, which measures the difference between f and u. G of x equals f of x minus u of x. This function g tells us how much f deviates from the secant line. Let's check the values of g at the endpoints. At x equals a, we get g of a equals f of a minus u of a equals 0. At x equals b, we also get g of b equals f of b minus u of b equals 0. So g is 0 at both ends. G of equals g of b equals 0. Tells us, if a function is continuous on a closed interval, differentiable on the open interval, and has equal values at the endpoints, then there must be some point c in a, b, where the derivative is 0. So we know that there exists a point c such that g prime of c equals 0. Let's compute g prime of x. Since g of x equals f of x minus u of x, then g prime of x equals f prime of x minus u prime of x. And because u of x is linear, its derivative is just a constant, u prime of x equals f of b minus f of a, divided by b minus a. So we now have g prime of c equals f prime of c minus f of b minus f of a over b minus a. But since g prime of c equals 0, that leads us to f prime of c equals f of b minus f of a over b minus a. And that's exactly what the mean value theorem states. What does it really mean, in fact? Imagine the graph of a function f, drawn smoothly over the interval from a to b. This function is continuous on the whole interval, and differentiable inside. On this graph, we look at 2 points. The point a, at x equals a, with coordinates a, f, a. And the point b, at x equals b, with coordinates b, f, b. Now, draw a straight line between these 2 points. This is called the secant line, and it represents the average rate of change of the function between a and b. The slope of this secant line is simply f, b, minus f, a, divided by b minus a. What the mean value theorem says is very visual. Even if the curve goes up and down, and twists in various ways, there is always at least one point on the curve where the tangent line, that is, the instantaneous slope of the function, is parallel to the secant line. In other words, there exists a point c, somewhere between a and b, where the function has a tangent line that exactly matches the slope of the secant line. Mathematically, that means f prime of c equals f, b, minus f, a, over b minus a. The distance between a and b is 60 kilometers. So, if we do the math, your average speed over the trip is 60 kilometers divided by 1 hour equals 60 kilometers per hour. Now here's the interesting part. Maybe during your trip, you weren't always driving at exactly 60 kilometers per hour. Sometimes you were faster, maybe 80 kilometers per hour on the highway. Sometimes slower, maybe 40 kilometers per hour in a village. You might have even stopped briefly at a red light. But despite all of that variation, the mean value theorem guarantees that at some exact moment during your trip, even if it was just for a second, your instantaneous speed, shown on your speedometer, was exactly 60 kilometers per hour. That's the heart of the theorem. If you travel over time with a certain average rate, there must exist a specific instant where your exact rate matches that average. So, whether you're a math lover, a student preparing for exams, or just someone curious about the beauty hidden in simple ideas, the mean value theorem shows us that mathematics isn't just numbers. It's about movement, logic, and even a little bit of magic. Sparkles, there's always a moment where theory and reality meet, and that's what makes math so powerful. Bullseye, if you found this explanation helpful or interesting, don't forget to like, subscribe, and hit the notification bell so you never miss a new math moment. Speech balloon, and if you have questions or want more topics like this, drop a comment below. I read every single one.